Hello everyone. So in the last class, we looked at the dissipation spectra and how it was behaving at different length scales. We started with the model spectra. We looked at how the model spectra behaved for the entire range. Then we looked at the compensated spectra in order to enhance the dissipation range. They emphasize the dissipation range, I should say. Then we looked at the dissipation spectra towards the end of last class, where what we looked at was the following, right? You had the dissipation spectra behaving like this. We saw where the peak dissipation occurred, and you just had to look at this one. This was the peak. Then we also plotted in this figure the cumulative dissipation, just to see where the bulk of the dissipation is concentrated in. And it turns out that if you just look at this particular table here, so we have the peak of the dissipation spectrum occurring at kappa eta equals 0.26, corresponding to L over eta equals 24. And then you have these cumulative dissipation values. So when it is 10% of its dissipation, it is kappa eta at 0.1 and L over eta at 63. And when it is 90% of its dissipation, as in total dissipation, then kappa eta is 0.73 and L over eta equals 8.6. So that comes from the figure, right? So, but what we had realized is that 10% to 90%, so that is 80% of the dissipation, occurs between 60 eta approximately and 8 eta approximately. So when L over eta is less than 60 and greater than 8, this is where the dissipation is concentrated in. So that's 80% of the dissipation. We are ignoring 20% of the dissipation. But what we said is that the bulk of the dissipation is occurring here. Okay? So earlier, a few classes back, when we talked about the dissipation demarcation length scale being 60 eta, as in that is where the dissipation starts, this is what we were referring to, because it is at 10% of the dissipation. So you ignore the 10% on the other side, on the energy containing range. Sorry, the inertial subrange and the energy containing range, right? So you ignore that and then you are at 10%. Only then is where your dissipation is sort of starting to occur, ignoring the 10%. The peak dissipation is actually at 24 eta. It starts at 60, but it takes a while to ramp up, and at 24 eta is where it actually peaks. Then it eventually dies down. And by around 8 eta, as shown here, by around 8 eta, the dissipation starts to really subside if you just ignore the 10% on the other side. Follow me? So 80% of the bulk of the dissipation occurs between 8 and 60. That was the takeaway from the dissipation spectrum. We will do similar analysis for the energy containing range as well. But before that, let's start with the inertial subrange. Now, what is plotted here? Again, a compensated 1D spectra. What do I mean by that? I had explained this in the last class. You have the 1D spectra for E11, E22 and E33, all three plotted here, top, middle and bottom, and they are compensated by multiplied by epsilon to the negative 2/3 and kappa to the 5/3. So this is that constant value that you get, right? This is that constant value that you get. If you remember, going back and just to refresh your memory, here we have this part here for the inertial subrange. If you take it to the other side, that's how kappa becomes kappa to the 5/3. Epsilon to the 2/3 becomes epsilon to the negative 2/3 on the other side. They multiplied by the E of k. And what do you have on the right hand side? It is C times these two functions. One function for the energy containing range and another function for the dissipation range, right? And then, so I am plotting that, and as you can see, I would get the value of C in the inertial subrange because Fl and F eta would go to 1 Am I getting that? It seems like from the figure that is what I'm getting. So I have a constant value in the inertial subrange, as you can see. The solid line here, okay, so here on the y-axis, it is the compensator spectra. On the x-axis, it is still K1, kappa 1, eta. The font is not very clear here, but it is kappa 1, eta. That is on the x-axis. The solid line is the experimental data, and this is from Sadoghi's 1994 data for boundary layer. The dashed line is the model spectra. The long dashed line is which one? The long dashed straight line. This is what we're talking about, long dashed straight line. Those are the values of C1, C1 dash, isn't it? A C1, C1 dash and C1 double dash, right? So C1 and C1 dash correspond to the inertial range spectra. And here the E11, E22 and E33 are the model spectra for R lambda equals 1450, 690 and 910 respectively, corresponding to the measured values of U1 squared, U2 squared and U3 squared. Okay, so I have the model spectra plotted, I have experimental data, and I have a straight line showing the value of those constants. Which constants am I talking about? If I go back, I am talking about these constants, the C1, C1 dash, C, C1 and C1 dash. Except here I have E11, E22 and E33. So I will not plot C, but I will plot C1, I will plot C1 dash. And since E33 is the same as E22 in isotropic turbulence, since E33 is the same as E22, I have the same constant C1 dash. So it's not C1 double dash, it's still C1 dash. So here what I have is, you will see in the inertial subrange, I have a constant. And that is not magic, it is the way the model spectra shows exactly that value. And in fact, the experimental data matches reasonably closely. As you can see, it is reasonably close to that constant value. So it is a single constant value in the inertial subrange. Everywhere else, of course, it will vary, because epsilon to the negative 2/3 kappa to the minus 5/3 times E11 of kappa, right, would be equal to that constant multiplied by FL multiplied by F eta. So in the energy containing range and the dissipation range, it's not going to be a constant. In the inertial subrange, it is going to be a single constant value. That is what you're seeing here. That is what you're seeing here. So just to summarize the observations, the second Kolmogorov hypothesis predicts a negative 5/3 spectrum in the inertial subrange. And with regard to the compensated 1D spectra, the Kolmogorov hypothesis predicts that this quantity adopts a constant value in the inertial subrange, which is what we are seeing. The model spectrum is showing exactly that, very good agreement with the experimental data. And the model spectrum would anyway show the constant value, because it is constructed in such a way that you get a constant value in the inertial subrange. The interesting thing is, the experimental data also shows something very similar. It shows evidence of local isotropy in this distinctly anisotropic turbulent flow. What do I mean by that? It's turbulent boundary layer flow, so it is an anisotropic turbulent flow. But E22 and E33 are very similar because of the local isotropy, right? And the plateau value of the compensator spectra is 4/3 that of E11. How did I get that? So if you go back a few slides, this 4/3 value should be familiar to you, right? Look at this. C1 dash is 4/3 of C1. That is where it is coming from. It is 4/3 of E11. So that constant is happening to be 4/3 of that value. That is what we are seeing. So a measured value of E22 of kappa 1 differs from the calculated value of E11 of kappa 1, even with the assumption of isotropy, but by no more than 10%. So it's still pretty close. That means the isotropic hypothesis still holds. we are showing through these model spectra and the experimental data how valid Kolmogorov's hypothesis is. And here, this is another example of showing that, this is another example of demonstrating that the measured value of E22 being differing by departing from E11 by only 10%, which shows that the isotropic assumption is reasonably valid for these high Reynolds number flows. So that is what we can gather from the inertial subrange. Our next topic is to go into the energy containing range. Okay, so here, so we saw the dissipation range, then we went to the inertial subrange. Naturally, the next thing to look at is the energy containing range. So the energy containing range is not universal. We know that. Okay, so the fact it is not going to overlap everywhere. However, what we can do still is that we can still scale it appropriately. So I have here the energy spectrum function in isotropic turbulence, and here I am not looking at 1D spectra, I am looking at the total 3D spectra. Because of its anisotropy in the energy containing range, it makes sense to look at the total spectra rather than a 1D spectra, because it is no longer isotropic, right? This is a range that is not isotropic. Everywhere else, inertial subrange and the dissipation range makes up for the universal equilibrium range, which is the isotropy assumption is valid there, whereas in the energy containing range the isotropic assumption is not valid. So it doesn't make sense to look at a 1D spectra, we will look at a 3D spectra. Alright, so what is shown here? It is the energy spectrum function in isotropic turbulence normalized by K and L11. L11 is the integral length scale. The symbols are actually experiments, which are grid turbulence experiments, okay, from Comte-Below and Corzine from 1971. And the circles are R lambda is equal to 71, so not too high. Squares are R lambda is equal to 65, again not too high. And triangles are again R lambda is equal to 61. So approximately the same Reynolds number, And that is why you see them sort of overlapping a little bit. Okay, not overlapping as in what you see in the universal equilibrium range, but they are very close to each other. They are not meant to be if the Reynolds number is much different. Whereas here, since the Reynolds numbers are similar, and that is why we picked these Reynolds numbers, we are seeing that they are pretty close to each other. The line here, okay, the line here is a model spectrum. The solid line, okay, the lines are the model spectra. Solid line is with P0 is equal to 2 for lambda, R lambda is equal to 60, and dashed line is P0 is equal to 2, R lambda is equal to 1000. Okay, so clearly you have the model spectra plotted at different Reynolds numbers. The dot dash line is the P0 is equal to 4, R lambda is equal to 60. So you can see where does the P0 come in. If you look at the model spectra, which we showed a couple of classes ago, this is where P0 comes in, right? In this energy containing range. And P0, we had discussed at that time that P0 can have different values. It can have 4, then it is called a one common spectrum. You can also have P0 equals 2. So we have tried those two different values and plotted the model spectrum here along with experimental data from Comte-Below and Corzine. So here you have it as so you have these symbols which are experimental data and lines which are the model spectrum. Okay, what are our observations? Now, unlike the universal equilibrium range, the energy containing range depends on the particular flow. We know that it is anisotropic. It's the energy containing range. It would depend on the kind of flow that you have. So it depends on the Reynolds number. Also, since the 1D spectra provides very little direct information because E11 of kappa 1 contains contributions from all wave numbers that are greater than kappa 1, what we need is actually E of kappa, because that would be the most informative for isotropic turbulence. And what you can do is you can obviously get that by differentiating the 1D spectra. You can get that. Okay. Now here we are scaling it by two different quantities. One is the turbulent kinetic energy and the other one is L11. The turbulent kinetic energy is obtained by integrating over the entire 3D spectrum, right? The energy spectrum function, if you integrate over the entire thing, you get K, turbulent kinetic energy. Now, the integral length scale is obtained by taking, 0 to infinity E of kappa over kappa d kappa, and that would be 4 over 3 pi K L11. So that is how you get the integral length scale. So K you obtain by just integrating over the entire energy spectrum function, and L11 you obtain by taking, you integrate E of kappa divided by kappa. Now, as you can see, the shape of the spectrum does not vary strongly with Reynolds number. We know that. For the model spectrum, P0 is equal to 4 has a slightly different shape than P0 is equal to 2. That is also expected. There's a 10% difference. What else? Now, I showed the energy spectra, right, which was scaled. We noticed that it does not vary too much with Reynolds number. It was scaled. But let's see now, by plotting the cumulative turbulent kinetic energy. And this is what I'm going to do. I did the same thing with my dissipation spectrum. And this is what I'm going to do. So for the model spectrum, I'll calculate a cumulative turbulent kinetic energy, which is K from 0 to kappa is 0 to kappa E of kappa prime d kappa prime. So basically the energy spectrum function integrated up until a certain point. And in this case, you are integrating it until kappa, and you are calculating the turbulent kinetic energy until that kappa value. And then you're plotting that cumulative dissipation against this L over L11. Just like earlier we plotted it against L over eta, here you're plotting it against L over L11 or 2 pi over kappa L11. Alright, and let's do some similar analysis. So as you can see, it is plotted here, right? And two different Reynolds numbers are shown. One is R lambda equals 1000 and another one is R lambda equals 30. It is on the x-axis, it is L over L11 and also kappa over kappa times L11. As you can see, since kappa is inversely proportional to L, as L is increasing here, kappa is obviously decreasing here because they are inversely proportional. Two curves are shown here just to show one relatively low Reynolds number and one relatively high Reynolds number. Also, the cumulative kinetic energy is normalized with the total kinetic energy, just to normalize it. So that's why it starts from 1. All right. What else? What can we say from here? Now we will do a similar table like we had it for dissipation. The peak of the energy spectrum occurs at L over L11 equals 5. The peak of the energy spectrum. Or kappa L11 equals 1.3. Let's see. The peak occurs at L over L11 equals 5. Isn't it? Isn't that what it said? The peak occurs at kappa L11 equals 1.3 and L over L11 equals 5. That is where the peak is occurring. So we don't have the energy spectra plotted here. But if the energy spectra was plotted, it would show something like this. So we would have to show it. It would start from here at L over L11 equals 5, or where is it? At kappa L11 equals 1.3. So the energy spectra is not shown here, but the peak will occur here. So that means you will have something like this. Since kappa is the kappa axis is reversed, the inertial subrange would be here. This would be ISR. This would be the dissipation range, isn't it? This is the energy spectra, E of kappa. This is the power law, isn't it? Kappa squared. So this is the energy containing range. Energy, ER as we call it, energy range. The inertial subrange and the dissipation range, isn't it? So the peak occurs there. All right. What else? 10% of the kinetic energy, okay, 10% of the kinetic energy is at L over L11 equals 6 and kappa L11 equals 1.0. That makes sense. L over L11 equals 6. This is where 10% and kappa L11 equals, what was it? 1.0. Okay, so somewhere here. That is 10%. And I want to go directly to the 90%. Occurs at L over L11 equals 0.16 and kappa L11 equals 38. 0.16 and 38. 0.16 and 38. So that would be somewhere here. This is where 90% occurs. So as you can see, this is 10%, and if I take it all the way up, this would be around 90%. It's very close to that one. So we have it as 10% to 90%. So 80% of the energy, right? 80% of the energy is contained in this range. 80% of the energy is contained in that range, meaning from it is contained between 80%, right, of the energy is contained between 6 and 0.16. So 0.16 L11 and 6 L11. So L between 6 L11 and 0.16 L11. In other words, it is contained between 6 L11 and 1/6 L11. Sorry, L11. L is capital. So my energy is contained in these length scales. 80% of the energy is contained between 0.16 L11, or that is 1/6, or that is 1/6 L11 to 6 L11. And that's it, right? So now you see where we got the 1/6 L11 from. If you remember, we had a demarcation length scale for the energy containing range. We said that below that is the universal equilibrium range. Above that is the energy containing range. This is where it is coming from. For a bunch of model spectra at different Reynolds numbers, we realize that 80% of the energy, turbulent kinetic energy, is contained in these wave numbers. And that is between 1 and 38. 1 and 38. Remember, in the dissipation spectra, we said that the LDI was 60 eta. 60 eta. And here what we are saying is that 80% of the energy is contained between 1 and 38, meaning 38 is the demarcation length scale for 38 is the demarcation wave number for the energy containing range. So essentially what we are saying is LEI is approximately equal to 1/6 L11. We already said that, and at that time I said let's consider this to be arbitrary, but here is proof for that. 0.16 is approximately equal to 1/6. That's where the 1/6 is coming from. And and kappa EI is approximately equal to 38. So that means that is the wave number. Kappa EI, I should actually say it is kappa EI L11, right? Kappa EI L11 is approximately equal to 38. So that is the energy demarcation length scale. It is at that point that the universal equilibrium range starts. Above that, below that in terms of Reynolds numbers, and above that in terms of length scale is the energy containing range. So that is what we have showed through this plot, that you have it, the turbulent kinetic energy is mostly contained in this range. Beyond that, the energy is negligible. So if we ignore 20% of the energy, 10% on this side, as in 10% on extremely high wave numbers and 10% on extremely low wave numbers, right? So less than 1, for example. So 10% is contained here and 10% is contained here, isn't it? So what we are saying is, if we ignore that on the extremely high wave number scenario and the extremely low wave number scenario, we will see that if you can get these wave numbers right, you can account for most of the energy, 80% of the energy to be precise. So that 80% of the energy is what we are after. And that is what we are summarizing here. So the energy containing motions are characterized by length scales ranging from 6L11 to 16L1. Isn't it? That's what we are saying. So 80% of the energy is contained here. Everything else is a very small contribution to the turbulent kinetic energy. So if you want to ignore that, you are only ignoring 10% of the energy. That's what we are saying. And this is the basis of turbulence modeling approaches that utilize something like resolving the large scales, like a large eddy simulation, where what they do is they resolve the large scales, assuming 80%, 90% of the energy is actually resolved. You're only ignoring 10% of the energy. So we will see that when we cover large eddy simulation, but this is the basis of all that. I hope this was clear. We will continue by looking at the transfer of energy in the next class. Thank you.